All right, we're back. Let's continue. So what did we do? Hopefully you've got some sense of electric charge. It's a property. Why? We're not saying why now. Do we even know? You can explore that later. But we know that if it has more or less electric charge, you'll get more or less electric force and so on. So we talk about fundamental particles. Let's talk about charge separation, so putting it to use. So there's understanding this on a theoretical point of view, like the nature of physical reality, and that's interesting, but it's also useful. So let's do this. And again, electrons, we're trying to make it concrete, at least in our imagination. It's hard to push an electron around with your hand. But one thing that'll be helpful is to realize, again, cheating, jumping way ahead of Ben Franklin, that when you rub objects together, something is going to lose electrons and consequently become positive, and something then will gain the electrons and then become negative. This object will also be gaining mass, which is a very insignificant, and usually we wouldn't worry about it, but it helps it be a little more concrete what's really going on. Okay, and there are other cases, but this is remember. So if I take fur or wool or hair, notice I've got that R capitalized, and I rub it with rubber or some hard plastics. I think of putting them in order, and I go from the fur to the rubber, and I transfer electrons. And I could put little e's for the electron, or I could just put negative signs. Okay, so if I put negatives, if I rub it right there, that's where the electrons are. Now, rubber and plastic are what? Insulators or conductors? Insulators, right? So the electrons are not going to be able to move from atom to atom. As much as they don't like each other, right? Electrons push each other apart. They can't get out of there because they're stuck there in the atoms for interesting reasons, material science, all that cool stuff. But they're stuck there. So if you ever play around with it, if you rub right there, that's where the electrons are, not over there. So they're going to pile up wherever you rub them. Okay, wherever you rub it here, that's going to create a place where there's a lack of electrons, and so I can make that positive, 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 which doesn't mean extra protons, it means a lack of electrons. I know you know that now. Also, these two are really worth remembering. So fur, rubber, put them in the order where the first letter here is the last letter here. The last letter, first letter. Fur, electrons go to rubber. Glass, the electrons go to silk. Okay? And so if I have a glass or even acrylic or whatever, then electrons are going to build up wherever I rub, and I'm going to lose electrons, creating a region of a lack of electrons. Again, losing mass, losing weight, and gaining over here is physically what's going on. So when people draw those positives, again, don't think protons. And don't think charges. There aren't charges, but what we mean by charges is electrical charge objects, as we discussed. Okay, and of course there's the whole triboelectric list. If you rub this with that, who gets the electron? They didn't know who got the electron, they just noticed that there was repulsion or attraction. Tribo, the Greek for rub, electra, the Greek for amber. Those are good things to know. Anyway, we can do this process also chemically. In chemistry, it's really about the combining, recombining, separating of atoms. Behind the scenes, there's all kinds of electric interactions. If you try to keep track of that, you'd never get any chemistry done, so those rules of chemistry would make a lot of sense. But if you have two types of metal, and you put an acid in between, you can get a flow. Now, if I have this picture where this becomes positive and negative, you know what's happening, right? What has to be happening is that those electrons have to be somehow taken off of here and put onto there. And they can just sit there until you touch and give the electrons a place to go. Because as they build up, they don't like each other, but they've got nowhere to go. And you can do this with two types of, you can use zinc and copper with lemon juice. Stick a lemon or an orange, lemon or lime, some citrus, right? Or you can do, if you have a filling in your tooth, and you bite onto some aluminum foil, and you have a metal filling with foil, and the saliva will create a flow of electrons, which will go into your nerves and not feel good. So batteries are interesting. And again, just thinking in terms of moving electrons. So now let's really do a little bit of more puzzles. And I'm going to say pause, and when I do, you will learn a lot more by taking the long, slow route, scratching your head as much as you can, until you come up with an answer that you bet $1,000 on, and then press play. And if you're wrong, just send I'll give you my address to send the $1,000. So here's a cool device. People were clever, right? They messed around, and now we've got crazy cell phones. You take a metal ball, and I really want to make a big one of these, and connect it with metal. So there's conductors, the electrons, there's some electrons, the free electrons that can move throughout. This is rigid, solid, and then I have this kind of foil piece looping down like that. And it's also metal, and they're touching. So I don't know if you can zoom in. Here's one electroscope. And there's a little piece in there, a little foil. If I go like that, can you see the foil there? And there's that little foil piece. And so they're attached. Okay, and so you can do a variety of situations. You can see there's a little foil in there. And that's an electroscope. And we're not going to measure amounts, but we're going to see the effect and try to think about this thinking. And I'll caution you about what you see often in textbooks and sometimes videos. So let's go through the sequence. I've got 4 main ideas, and the professor might give you more. Here's a puzzle. I'm going to take fur and a comb. Think rubber or plastic. Fur and a comb. I'm going to rub them. Then I'm not going to touch the electroscope. I'm going to start with a neutral electroscope. One way we do that is to give any free electrons a place to go. That's called ground. And I touch it, it's neutral. So it's just kind of hanging there. Okay? Now, so I'm going to take the fur and the comb, rub them, and we'll see which one works. And for maybe wool, sometimes wool works better. Our fur is kind of running out. I can use my hair. It's all animal hair, right? In a sense. I don't know if there's a difference for your hair or whatever. Okay. And then I'm going to bring it near without touching. Pause, predict what happens, and say why. What happens inside the metal? And what does the foil do? Pause, predict. $1,000. You did it? Okay. So here we go. What happens? No, because that's just the whole lot. So let's see what happens. Has this got extra electrons or a lack of electrons? Well, now you wouldn't know. Who would know? Ben Franklin didn't know. He didn't even know about electrons. That was like 1800, right? He didn't know about electrons till the mid 1800s, right? So, J.B. Thompson, remember? So, but this is getting electrons. So it helps the cheat a little bit. So it's got extra electrons. Negatively charged. That's why I like the black one, even though the red one is negative. I bring it close. Interestingly, oops, this guy, my battery. I forgot to show you my batteries. Dead battery. Probably also a dead battery. All right, here we go. Cool. Let's see what happens. Extra electrons. The electrons in the electroscope, do they like? These guys are going to go, oh, hey, what's up? Let's go hang out. Or are they going to run away? Electrons. Repel electrons. Can you see it? Can you see it? Yeah? Good. So you get over there. Where did the electrons go? down. Right? So I'm pushing electrons down, and watch what happens when I take it away. They come back. Why? Because they don't like each other. They get as far away as they can. Now, if they can't get away, they're there. So here they are, pushing electrons down both sides. So remember to think of the physical. So I bring this next to it, or a cone, whatever it is. And think of the teeth as being negative. That's good, right? So I got extra electrons. These electrons here going, whoa, whoa, I'm getting out of here, I don't like you. And they head down, electrons head down. And they build up over here, but they're going, I don't like you either, but I don't like them, so where am I going to go? Oh, wait, here's a place to go. I'm going to go over here. And this builds up. And then they go, oh, I don't like you either, but that foil can float. So these guys push all these extra electrons, which I'll symbolize with just a negative sign, extra electrons, will push each other away. This drives the electrons down into the legs of the electroscope. These two are negatively charged and they repel. Interesting, you see something that happens. The closer I get, the stronger the force, the more I can push down and the more I can repel. So these are the things that the early researchers had to figure out without knowing about electrons. So clever folks, right? And then when I take it away, well, notice that I haven't added electrons. So what you'll often see is this. Are these protons? Those aren't protons. You'll even see people showing positives moving. Protons don't move inside metals, right? That's nuclear reaction. That's a lack of electrons giving a positive ions or positive atoms, okay? So the electrons have gone down, leaving a positive region. But the entire thing, now this is important, is we want to say that this is all still neutral, but it's polarized, meaning that there are two regions. There is a positive region to the electroscope and a negative region to the electroscope. And we'll explore what you can do with that. So we're cool with that? If I take the comb away, the electrons say, I'm out of here. They spread out as far as they can, still neutral. And as you saw, let's do this one more time. Good. Electrons, imagine, it's abstract, but imagine somehow, I haven't said how, got a lot of electrons here, transferred here, lack of electrons, extra electrons, pull it in, pushing electrons down. If I did that enough, that electron movement, current, electric current of electrons moving would actually warm the metal. There's actual motion within the atoms. We can't see that, so it's like it was a mystery for so long, right? But that happens, and I let it go, and those electrons go, well, I'm out of here. Let's go up to the positive region, spread out. So does that work over here to glass and silk or acrylic? I think this one looks better. Let's try. Some get more charged than others. There's silk that's worn out here. So now, what is that? Positive or negative? Who got the electrons? Glass, silk, silk, glass. Electrons went here. Or did they go here? Glass, silk, silk ends in a K, and glass, it's got to be glass to silk. Do it a few times, you'll get it. I know it's confusing. But the electrons went to the silk, having this a lack of electrons, are positive. So here I'm going to take this guy and use it. So I'm going to move this guy, now positive, which has lost electrons, positive ions, right? And move it next to my electroscope. So pause, predict what happens inside the electroscope, and predict what happens to the foil leaf. And you pause. Very cool. So what do those electrons do? And of course, I bring it kind of more like that. Do the electrons in here go, oh, look at that, cool, it's, I don't know, Miley Cyrus, whoever you like. Maybe Jimi Hendrix, because A, he's dead, and if he's there, that would be really cool. But, ooh, the electrons go, let's head up here, and they head up from this part, and we get a whole bunch of electrons building up. But they also head up from that foil. And that leaves this region a lack of electrons and also a lack of electrons. Hold it. These two are the similar, same charge, positive, and so they will still push apart. And a very similar look to this, but look how different that is. This one's gained some stuff, this one's lost. This one's gained, this one's lost. So think that through. It'll help you with all the other more complex applications. Let's give it a try and see if it works. And now my rod is pulling electrons up. I'm pulling electrons up because I've got a lack of electrons, so positive ions, pulling the free electrons up, leaving a positive leaf and leg. Still, the whole thing stays neutral, but polarized in an opposite way that I had before, because here I've got polarized positive and negative. Neutral, but polarized. So think of that whole unit being neutral but polarized, okay? And when I pull it back, the electrons are going to go, oh, I hate you, go on over here. But you know, you're seeing whomever, Steph Curry, whomever, you go, hey, and then you want to get out of there. Okay, so again, let me do that again. Glass, silk. The electrons went here, lack of electrons, attracting the electrons up, and then they fall back. Neutral. Here, this gets the electrons, so this is part of the difficulty. You get pluses and minuses all over the place. You got to keep track of it. Now I got extra electrons here, negative. I'm going to push electrons down, polarizing it, negative, positive. The electrons are there. They really like each other, but they really don't like this. And then I let it go, and they distribute back again. Push electrons down, pull electrons up, and polarizing this conductor material. Okay, so those are two puzzles. Make sure that that's clear. Think it through. It's confusing at first to keep this stuff straight. All right, so next, I want to, I'm going to do something similar, rub, and then touch. Number 3. We're just going to rub these guys together, transfer electrons, then touch. Refer to the comb, the rubber or plastic is going to get the electrons. Negative, black, something like this, and then I'm going to actually touch. Teeth of the comb being like negative signs, a lot of extra electrons here. And when I touch, what's going to happen? Well, remember that this is an insulator. And so the electrons don't come off too easily. You've got to rub them off. Okay? In all these cases, these are insulators, so you have to rub them off. Let's see if we can do that. And then I'm going to rub some electrons off. And then what are they going to do when I move the cone away? What happens to the leaf? And where did the electrons go in the conductor? Pause. Okay, $1,000. You got that. Here we go. Getting the electrons. Getting the electrons over here. Going to. Let's see if I can do this. When it's humid, it's hard. Get some, right? You see that? So I've put on some electrons. When I rub them on, here they are, and they go, oh, I'm free. They're free electrons. They go, I'm getting out of here. I hate you. I had to stay with you, but now I'm down. And where do they go? Down there, and down there. Negative, 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 negative. And the leaf pushes apart, and I take it away, and now the electroscope has a net negative charge. So the E-scope becomes negative overall. And the free electrons will spread out as much as they can, and when they're down here, they'll push apart. And up here, some start going down, and they go, oh, I don't like it down there, I don't like it here, and just at some point they stop moving. We call that electrostatics, static situation. First they move down, then everything is balanced, and there's no motion. It's an important idea. Okay, cool. Now what happens, this is interesting. Let's look at this guy again. Remember, there's all kinds of extra electrons on this thing. And now I got extra electrons here. What I'm going to do is push some more electrons down there. They didn't want to go down there because there's a bunch of electrons. But they really don't like my electric cone here, right? So I push more electrons down. More net charge creates more force. Does that make sense? I got more electrons down there. Now they're really feeling jammed and claustrophobic and everything. And some of them get out there, but then they're built up here, so some stay down there and down there. Okay, now watch what happens. Taking electrons away. Positive. Whoever your favorite musician is, let's say, or actor or actress. Here we go. Ooh, the electrons like this guy. Where are they going to go? They're going to come up. And now the electrons have left here because they go, ooh, this. I know I don't like being up there. There's all these electrons, but I sure would like to go see this famous acrylic rod. So they go up, leaving these neutral. Those extra electrons went up here, creating lots of electrons here and a neutral environment down there. I move it away, and they go, oh, I'm getting out of here, it's crowded. Visualize the movement of the electrons. Okay. Now, if I do the same thing again, but I'm going to use glass electrons itself, and I'm going to touch it, and what's going to happen there is that I will, as you can imagine, take that now positive rod, rub it. They're attracted, and now they get to go hang out with their favorite celebrity. So they'll leave, and then I take it away, and what have I got? Well, what's happened here is that the electrons have, again, headed up. It was a neutral electroscope. Electrons have left the object, leaving it a net positive, not protons, but positive ions. And of course, these have a similar charge, so they'll repel. Let's see if that works. Do it one more time. Make this neutral. Any extra electrons can come to me. If it's lacking electrons, I'll give it electrons. Let's hope it works. Yes. Now, hopefully I can rub it so that I'm grabbing electrons, right? I'm taking electrons up. Grab some electrons. Okay, that's a bit. So I took some electrons away, leaving it positive. If I bring a positive in, then the electrons go up, making it more positive, more repulsion. If I bring a negative in, I'm going to shove some electrons down and neutralize. If I bring a positive in, it'll pull more electrons, making it more positive. Positive in, bring more electrons, separate. A negative in will push electrons down and tend to neutralize, let's see. And so less net charge, here it is. Are we good? And they come together, they take it away, and they spread apart. Here, it's negative. I'm pushing the electrons down into the positive legs, neutralizing it. Take it away, electrons go back up. And if that process makes sense, you're getting it. You can talk about electric current and wires and things like that, thinking about this sort of thing. Now, we've got, I'm not sure how much time we've been, doing this?
This was 30 minutes.
30 minutes, so long discussion. It's really about this, okay? You can always get your pause. So, one more thing, and that is grounding it. So, it's similar to this. So, number 4. Grounding by touching with a finger. So the sequence is like this. Start out with a neutral scope. And then I'm going to bring in either one. Let's see what worked better. Probably the comb. Negative. Without touching. Don't touch. You know what happens? The free electrons say, ooh, I'm getting out of here, making this negative, and the free electrons go down there. And then what do? Then I come in with my finger and I touch. What you also have to realize is that free electrons, at some point they go, I don't want to go down there, there's too many electrons, but they will come from here to here. So you get a region over here of free electrons as well. And they're not happy being together, but they're less happy being over here. If I come over and touch them, they'll leave. Does that make the electroscope positive or negative? Then, when I remove my finger and then the comb, what will happen? Pause, predict. Now it's true, my finger is not a conductor, it's an insulator, but still, some of them are going to come over to my finger. Right? And so let's see what happens. Let's see if we can replicate that. Adding electrons. Make sure it's neutral. Adding electrons. Pushing some electrons down. Giving a place for them to go. Ah, I got some electrons. Take it away. I took away electrons. The whole thing is now positive or negative? Positive, meaning a lack of electrons. I didn't give it protons. And we have repulsion because of the positive situation. It's also true when it's positive that if I touch it with my finger and it's lacking electrons, I can give it electrons and neutralize it that way. So this concept of grounding something with a buildup of extra electrons or lack of electrons through contact with something that's sort of a reservoir, we say, of electrons is a powerful idea. So real quickly, I think I will leave the, well, let's do it. Let's do it real quickly. A balloon and a wall. Now, I have a feeling this is not going to work. That might work, okay. That works, but it depends on the, you ever see a balloon stick? So I'm not going to take the time here to do that. You can try it. But why does a balloon, conductor or insulator? The word right, oh yeah, insulator, right? What happens? Oh yeah, fur or hair, electrons go here. You got extra electrons right there. You got to know where you rub it because they'll sit there. And then you come over here. This is neutral. So when you take a balloon and you go to a wall, and things in the room are neutral, that's otherwise you'd be getting shocked all the time. Sometimes you do, especially in dry areas like Arizona, you get shocked all the time, it's annoying. And you bring yourself a blue balloon, and you go here and you rub it, so you add electrons to your balloon. And you take that part that has the extra electrons, turn it to the wall. A region of extra electrons. And you find that it attracts. Why does it attract? Well, usually a wall is going to be, again, not a conductor, but an insulator. And what happens is, within that neutral, the atoms, let's exaggerate the atom. We just exaggerate this. The electrons don't like other electrons, so they're pushed away to this side of the atom. And it's a very small effect, but there's a lot of atoms. So it does add up to a real effect, a macroscopically measurable, leaving a polarized neutral atoms where, what's stronger, attraction or repulsion? Hang on a minute. Since these are closer, the attraction is greater than repulsion, giving a net attraction whenever you polarize. Now, if I bring something positive in here, somehow I take electrons off the balloon, I bring it positive. Let's just say that. Let's say somehow I rub it with something that takes electrons away. And now I got a lack of electrons, not protons. What happens inside that atom? Well, then the electrons are going to say, cool, check that out. Let's go over here. And the atom will sort of, will polarize, stay neutral, but polarize. And again, the attraction, because these are closer, will be stronger than the repulsion. So when you have attraction, you don't know if it's because you have opposite charges, or maybe something has net charge, and the other thing is neutral, but polarized. And that's tricky. So think about that. And you have to do a sequence of experiment. And so Ben Franklin was good at being organized, but he didn't know this whole thing about electron, who's got the electron. Quick, finish this off with a related topic. Let's go to capacitors real as an introduction. We can use all of this idea of separating charge, which usually means transferring an electron from one to the other, holding extra electrons, having a lack of electrons, in what's called a capacitor. So we say we hold the charge separation. Again, charges aren't a thing, but we're talking about the electrons. Or we store it. And we can do that by taking electrons from one plate on the conductor and moving it to the other. If I touch, of course, they're going to neutralize. So I put something in between, which will be called a dielectric. Now we'll see that we can do this. Now what's so great about that? Well, if you do charge this up, which means somehow with a battery or however you do it, you're moving electrons from one to the other, one plate to the other. Then you touch it. That can be very dangerous. There can be a lot of energy stored, if you will, in these capacitors. What do you do when you take a flash? When you take a picture, if you use a flash, there's some source of energy that gives it boom, that flash. It's a capacitor that's inside the camera. So capacitors are very useful for large bursts of energy. And your electric company has huge capacitors to store that charge separation to a variety of means that you'll learn in this course. So we have this idea of simply parallel plates where looks kind of like a battery. In fact, the symbol is often two straight lines or maybe one curve. This is a parallel plate capacitor, and you can tell that this has got a lack of electrons and excess or extra electrons. They've been moved this way. Turns out you get more capacity if you move the plates closer together, but then if they touch or they jump, that's a problem. So what you do is you get them close together and you put in between them non-conducting or an insulating material called a dielectric. You'll learn about that and worry about it now. But like a little film like this or something. And then what you can do is you can take them and roll them up. So imagine two pieces of paper separated by a colored piece of paper, and you can roll it up. And then you've got this nice cylinder of these positively and negatively charged plates, not touching, so separated by some material, and you have these cylinders. Oh, can we have a second? Are we done? Or
no.
We're still going? Good. There's other designs, and you'll explore the details because really the glory is in the details. And so now I want to show you something fun. If you've hung in there, or feel free to pause it at your leisure. Very, very useful to be able to store energy or supply energy through this charge separation. Here is what I like to call the extreme rubbing device. It's kind of a tricky, actually, thing. It's called a Wimshurst machine. What I'm basically doing through, again, a fairly complicated setup, but you know the idea. I'm taking electrons from one side and putting them on the other side. So I can do that and build it up. So I'm moving electron. I can't tell which. I don't know, right? So somehow one's got extra electrons, one's got a lack of electrons. If I go and touch them, I'm going to get a shock. It won't be lethal, so I'll be fine. It'll feel like a rubber band. Let's see if I can do it. As it gets closer, the force gets stronger. And they pull. And then the electrons that are built up and they hate each other, they got a place to go. And they jump the gap. And as they go through the air, they make the air give off light. And if I keep doing it, well, it's just fun. Lightning, right? So that's a capacitor gone wrong. Right? Sometimes you want that spark, right? That's good. You build it up and then spark. Otherwise, you create that separation. You hold on to it until you come up and say hello to your friend. Say, hey, how's it going? You do whatever you do with the electric force. And so this is the fundamentals of the electric force. We'll build on the magnetic force. I hope it's a little more concrete to you. Know that people didn't know what was going on, so it's okay that it's confusing to you. But keeping track of the electrons is such a helpful thing. The next thing we're going to talk about is the invention of the concept of fields. Gravity fields, electric fields, magnetic fields that Michael Faraday added. How is it that one thing attracts or repels another thing without touching? So he made up this idea of fields. Turned out that was a very, very useful idea. Again, abstract because you can't see it. We're going to write a lot of equations that describe what makes electric fields and what makes magnetic fields, how strong they are, in what direction. And that's the course of study of electromagnetism. So cheers, we'll do fields another time, and then we'll get into build up the mathematical framework and start doing some puzzles. Remember, you can't learn physics without doing problems.